수업 시간에 안 보고 비디오 보고 공부하니까 보셨지? 좀 활용해봐. Okay, interestingly, mass spec, usually we call mass spec, but it's not mass spectroscopy, it's a mass spectrometry. The reason we're going to talk about it later, but anyway, that's called as a mass spectrometry. Not microscopy, not tomography, but mass spectroscopy is a technically wrong term. Mass spec can detect only charged ion molecule. It cannot detect neutral molecules. So that's why mass spec need to make the molecule into charged species. In electric field, if the charged molecule in electric field, it follows those electric field, moves to the opposite direction, right? Positively charged one goes to negatively charged electrode. And not perpendicular, it's following that electric field. And if that charged molecule is inside magnetic field, if it stays, then it doesn't move. But once it started to move, then there is a force of Lorentz force applied, and it gets the force perpendicular to the electric field, right? FBI, force, electric field, and magnetic field. So through this direction, it gets that force to the perpendicular. That's why it's a continuously moving like this circular motion it makes. So basic principle of a mass spec is shooting the charged particle into magnetic field. Then it moves to curve the motion, and then depending on those mass size, it goes make different the distance of the diameter, and by measuring that diameter, we can get the mass of the molecule. That's the basic principle of a mass spectrometry. Okay, so there are electric field, magnetic field, charged particle. We don't have magnetic particle here, but this is utilizing the basic physics, the principle, and then we can get this neutralized. Okay, so that's why if it's a neutral molecule, making that neutral molecule into charged the species is the first step. So all the mass spec, they need to have first step of ionization tool. Ionization can be done by removing one electron or by adding electron. Then it can generate maybe plus or minus. Either way you can detect. Okay, in plus it can move this way. Minus it can move the other way. Except that difference, then you can discriminate that this is positively charged, this is negatively charged. And here, ionization method, this is ionization as the electron spray ionization. And TOF, time of flight, quadrupole, ion trap, this is the second step. After I'm making the ion, and then how you can make that travel Time of flight is shooting and then measure those time. And then by measuring those time, and you can detect the mass. Quadrupole make dipole is 2, is dipole. Quadrupole is 4. So it's moving, this motion, and then moving the flying, and then get those the signal we can get. Ion trap is applying electric force, electric field, capturing those ion again. So these are all analyzing. This is ionization method. Okay, ionization method is just historically the first one is electron impact. By shooting high energy electron and shoot those molecules, shoot it into the molecule and break the molecule, and either positive or negatively charge the species. It's a very harsh reactions. Next to the electron impact, then now chemical impact. That's a little bigger molecule. It's a little milder. The next one is fast atom bombardment. That's on the surface, and it hit to the surface and generate the ions. And more, we need to have mild deionization method without breaking the mother ion. So MALDI is the next level, matrix assisted laser disruption ionization, not directly attack the molecule. By putting laser energy and on the matrix, and molecules are on the surface, and then transfer the energy to the molecule, and the molecule get energy and then get ionized. So that's a little milder condition. And ESI is the mixing together with the acidic solution, and then spray, and then let those charged the bubble traverse and dry it out and explode, and smaller and smaller eventually gets a single ion, and then it can reach to the analyzer. So this method now, when I was a graduate student, FAB was the most advanced technique. Now after 20 years, ESI and MALDI, these two techniques is most common at the moment, because it can generate, it provide most stable ionization method. Usually it does not break the original molecule, and it can save those original molecule, and you can get original mass rather than fragmented mass. Okay, and here analyzer. This is analyzer, very original the method of magnetic sector. Big magnetic field, and then moving this way or this way, right? So if you have one magnetic field, magnetic sector, usually size is huge, almost the size of this room. Then one side you have this, the flying ring, then positive one you can shoot this way, right? Then negative one you can get the other way. Then you need to have 2 rooms. Then you need to have a big space. If you want to save space, how can you change the format? If you have a positively charged ion, if you shoot into the magnetic field, it travels this way. Negative ion travels this way. Then you need to have 2 space. That's waste of a lot of space, right? Very expensive way. How can you change? Or how can you make it simpler? Half a space to measure both positively charged and negatively charged. 아이씨, 누가 좀 답 좀 해봐. 오늘 사탕도 안 가져오네. 코인도 안 가져가고 외상으로 코인 준다. Magnetic field, magnetic sector is very high resolution mesostat. The problem is it occupies too big space. Okay, so if you shoot positively charged particle, it moves this way. But you want to measure sometimes a negatively charged one too, but it travels the other way. Then you need to have 2 rooms. With the space-wise, there's too much waste, right? So how can you make this simpler, using smaller space? 이거 좀 좋다 좀 해줘. 어?
동시에 양이온과 음이온을 동시에 측정해야
동시에 측정하는 건 어려워.
그 마그네틱 필드 정렬
그렇지. 마그네틱 필드 방향을 반대로 하면 이쪽으로 가던 게 이쪽으로 갈 거고 저쪽으로 가던 건 이쪽으로 가겠지. Okay? So by just simply changing the magnetic field, you cannot measure both positive and negative, but you can change. One time you measure positive one, next time you measure negative one by changing magnetic field. Because of this perpendicular direction, if you change that, then the applying direction is changed. Okay? 나중에 줄게. 오늘 안 가져왔네. 내가 이 문제 내려고 할 때도 이렇게 장황하게 설명했어요. Okay, good guess. HPLC is a chromatography, right? High pressure or high performance liquid chromatography. So HPLC separation, you get liquid sample, then MALDI and fat. Then you need to observe on the surface. You need the matrix. You need to get those sample and spot on the surface. So you cannot go directly into the mass spec machine. ESI has electron spray. It can be mixed together with the acid and it can directly enter to mass spec. Then you can get those mass spec signal continuously. Okay, that's why ESI can be the powerful in that sense. Both of them are ESI and MALDI. Both of them are milder condition, but MALDI is used to make a spot, and ESI can be directly injected. So that's why those two is the most popular for now, but you need to understand why they are different in the formations. Okay, good. So to get to the mass spec, you may have heard the mass spec names. The first part should be analyzer name. Ionization method name. Second part is the analyzer name. So those are combined together. So then ESI quadruple, ESI TOF, all make sense, right? Here, which does not make sense. And ESI MALDI, both of them are ionization method, right? So it doesn't make sense. So you should have one ionization method and the other side should be analyzer, those are separated part. So that is the name. So then now, if you hear the name of a mass spec, MALDI TOF, okay, ionization is done by spotting of the matrix, and then separation has been done by time of flight. 그 정도 알아야 아는 척 할 거 아니야? Okay. Tandem is connected, two mass. Okay, ionization is just one method. You choose MALDI or ESI. Analyzer, you can separate one, and then you can select one ion, and then put it back into the second ion by breaking it. Then you can get the further informations. That's a tandem mass. Okay, TOF possible. You can add one TOF and get one signal, one ion, and then inject another TOF. That's a possible. Q-TOF, quadruple TOF, also possible. Ion trap MALDI, I just change those order. You need to ionize it first, and then separate it. Okay, this is not tandem mass. Triple quadruple, Q, quadruple. Usually you may think it's a two quadruple, but second one is a breaking part. First one separate, and select one ion, inject into the second one, break it, and then inject the next the quadrupole. So that's commonly used of TQ or triple quadrupole. 정확히 몰라도 대충 이름은 들어놔야 그 메스 스펙을 한번 공부를 했는데 수업 시간에 배운 건 아니지만 이렇게 써머라이즈 하는 거야. Okay, if you use mild ionization method, you do not break the mother ion, so you can get original mass. And if you look at your textbook, there's a lot of fragmentation pattern. How it is fragmented, utilizing that information, you can guess what is the original molecule's structure. But this method, maybe 20, 30 years ago, it was quite important technique. These days, not anymore, because there are more powerful techniques, so-called NMR. So we are going to learn later. So using NMR, you can get those information much easier. That's why this method is not much used for now. But still, we can get that information. In tandem mass, you can get fragmented information too. So peptide sequencing is mainly this one. Fragmented, charged one you can get. But again, I want to underline, stress that fragmented neutral one you cannot see. Mass spec only can see charged one, not neutral one. Okay? Okay, organic chemistry. Good. So double bond alkene nucleophile, which has more electron, it attacks electron 4-1 acid, capture acid, and release halide. Halide comes back and bind it to the positive charged one, generate alkyl halide. So that's what we have learned in the last lecture. Alkene attacks acid first, and then release Cl minus, and Cl minus and water may compete. But in water is a large excess, and that next step nucleophile is water attacks first. So you see alcohol. That example we have seen in the last two. Okay, same way, the first one was the acid there, and acid generates the proton, and then alkene attack that proton, captures, and then generates carbocation. And then, which was a nucleophile here, in this example, there's no other nucleophile other than I minus. So that's why I minus attacks. Okay, if it's a step-by-step reaction, now we are going to move into the real reaction of alkene. Today, a lot of reactions we are going to learn. So that is basic. Small thing we have learned in the last class. So let's just see. So this is the collections of reactions. Now first, the functional group in organic chemistry. Alkene can do many different things. Most of them looks like it's an addition reaction. Okay. By adding something, XX or XY is added one by one. It can be done by synergistically together like this or stepwise. So the example I just showed you was the stepwise, right? Acid was added first and generate intermediate carbocation, and if that carbocation react with another nucleophile. So let's see. So in this case, this example, just simply see. Here, starting from this, the HBr, and then strong base attack here, and then push this out, and this is the opposite reactions. Elimination. Don't worry about much. This lesson we'll learn much later in the next semester. And another case, if you have hydroxyl, and if you add the strong acid, then this hydroxyl group can be removed, and then moving back to this the alkene 2. So this reaction can be in a sense, this is the equilibrium. This one, by adding acid and water, it can go this way too. Now if this reaction happens, okay, so in this case, this one by adding acid without water. If you add water, then you can come back to this product. Then, if by adding this, what product can you expect? Water is removed, and then double bond can be generated. What product can you expect from this? Water is removed here, OH, and then you can take one proton here, 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 right? So you may have three possible products, double bond here by removing this, or double bond here, or double bond here. There is a possible product you can get. So this is just an intro. Now real the reaction for today. Alkene with halogen. In the last lecture, we have seen HCl, HI, right? If it's a CO2, halogen molecule, and product is this. Seems like two molecule is added to this. Seems like it is added double bond here, and ClCl to Cl is added to the double bond, looks like. Maybe that's one possible way too. If it's equivalent to 2, 2 pi electron here, and then ClCl can be added like this together. That's also one possibility. But another possibility is ClCl or BrBr is originally there was an equivalent, but that electron can be shifted to one side, and this electron can attack this side first, and then push this out. This reaction is similar to reaction with the HBr, isn't it? In the case, H was positive, that's why H was captured first, and then generate the carbocation, and then Br comes back, right? The product was HBr, but in this case, BrBr. So that means this bond is also, it does not prefer the homo cleavage. Homo cleavage requires a lot higher energy. Br radical versus Br minus. Br minus is much more stable. So this is also possible. Attack here and then push this out. Electron, 2 electron is moving. And then push this. And then this is pushed this way. Electron moving this way is much natural. This electron is moving same directions. Moving this way, it comes this way, that is not preferred. If it's perpendicular, that's also one situation, that doesn't happen. So going attack here, the next electron also moves to this way. This is more natural flow. Okay, so this reaction can happen. Then evidence whether this is maybe the right mechanism or original one, maybe parallelly attacking together. Two possible mechanisms, but here's the evidence. If you add this BrBr to this cyclic alkene, this one is formed, this one is not formed. Using this, can you guess which mechanism is more reasonable mechanism? Chemistry is by just drawing very simple reaction like this. It's difficult to say which one is correct the mechanism, which pathways it goes, but by the observation of the product, by looking at this product, this does not happen. This does not the form. Only this is formed. Then maybe reasonable the explanation is. Maybe first step is this attack and forms this kind of intermediate, kind of cyclic intermediate. And then second bromide comes back from behind and attack here and same direction, this is move out. Positive, negative. Maybe originally, if this is ended first, then maybe you can say the positive charge is formed here. If positive charge is formed here, then this kind of the selectivity may not be obtained. If a positive charge is formed here, then there is a carbocation. What is the configuration of that position? sp2 or sp3? Carbocation. sp2 is a planar structure, right? If it's a planar, then approach from this side to this side is almost equivalent. If it's equivalent, then your observation should be half and half of this. Right? That makes sense, right? But this is not formed, and only this is formed. That's why it can be postulated, it can be imagined, maybe there is this kind of a bridge like intermediate is formed, and then Br minus comes back from behind and push this out. That's why only this trans product is formed. That's a reasonable guessing, reasonable imagination. Has not been proved for a long time, but so the mechanism is, explanation is by forming this kind of the cyclic form bromium of the intermediate and then attack from behind. And this hypothesis was proven by one chemist, so-called George Olah. He worked on stable carbocation. So difficulties of this original the work was there are good nucleophile, then you cannot stop the reaction in the intermediate state. So to remove that good nucleophile, he used this system, and then utilizing this fluoride affinity to Sb, and then this one is removed. Then there is no good nucleophile in this system. That's why he could capture this intermediate in the SO2 solvent. And then he proved that the structure of this one is really existing. So sometimes there is unstable intermediate, or even similar to the transition state. If you can capture them in a specific conditions, then you can prove whether that condition, that the mechanism is correct or not. Okay, so Cl2 or Br2, if you add to this alkane double bond, it can form this kind of bromium, or if it's a chloride, then chromium. The intermediate is formed, and then if there is good nucleophile around, nucleophile comes behind and then push this or push this, and then open this way. Okay. If there is halide, then halide attack will happen. If there are large excess amount of water, then water will attack. Okay, that reaction is here. So let's say you have halogen, Cl2 or the Br2 or I2. And then it can activate, it can form intermediate. But if you have at the same time large excess amount of water, then that intermediate will react with water first, and they can generate hydroxyl and halide. And this product is called halohydrate. Okay, so this is two-step reactions. Previously, last week, we have studied acid activation. In this case, halogen activation. Neutral halogen by providing one, and then the other side becomes negative. Negative is more stable, and first one is electron is donated, so this one is positively charged, forming intermediate and then form this kind of product. So mechanism explanation, as I said, by adding this, one generates negative stable one is participating in this bridge structure, and then water attacks behind, and then same reaction pushes this out. Relationship of these two positions, Br and OH is a transfer-cis. This is what transfer-cis. 아무도 답을 안 한다. 뭐라고 했어? 못 들었어. It should be trans, right? Because same way, it should attack here and then push it this way. One is up, one is down. There should be trans relationship. Okay, by the way, this BR2. BR2 is usually quite reactive. Reactive means toxic, and especially it is known to be very bad to men. It can make the man set up. Prim can generate. So BR2 is difficult to handle. So that's why this reagent is developed. So-called N-bromosuccinimide, so-called NBS. NBS is stable, slowly generate a small amount of BR2. So NBS, if you see, is a convenient reagent to replace bromine. Okay. If you have the NBS, you can assume this is similar to BR2. BR2 here and water here. Okay. Same chemistry, we have the same. Activate this one bromium, and then water attacks, and then open. If both sides are the same, then there is no selectivity. The same property we get, but this one, this carbon and this carbon is different, right? Last week we have learned about the Markov-Nikov rule. Markov-Nikov rule says in acid activated system, which one prefers the attack? More substituted carbocation is more stable, and that position is attacked by nucleophile. Right? In this case, which is nucleophile? Hydroxy is nucleophile. Right? This is similar to proton in the last week. So that's why this OH attack should happen this more substituted position than this one. Makes sense, right? Then in this reaction, this also makes sense. These two positions, here and here, this position is more substituted. And then BR2 activated here, and water attack should happen this. Then this product is Markov-Nikov product. Looks like both of them is a substitution, Br and OH, but you should think which one was second attack material. Okay? So this is a Markov-Nikov product. Okay, moving to next. We learned the two. If you add H2, the X2, then XX added, but not at the same time. One X added first, then the other X attack behind. That's one. Second one, X2, but nucleophile was water. Excess amount of the nucleophile was water, so product is X and OH. That is the product. Now, if you add acid, this is the reaction we already learned last week. Acid activation, so proton is added, and then carbocation is formed. There is no evidence here the cyclic are formed. So this one may generate the the more stable, more substituted carbocation, and then water attacks. So water added. Look at the reaction condition. 250 and high pressure maybe, and then the phosphoric acid, sulfuric acid is very strong. The acid, which is difficult to use in the laboratory. So it may be industrial scale. So to use this chemistry in the laboratory, we may need to discover or develop milder condition, in HA condition. That option is to replace this acid, strong acid, utilizing mercury. Metal cation is acid or base. Metal cation is acid, similar to proton. Metal powder, reductant, not base, because it donates the electron forever to the partner. That's a reductant, right? So mercury, charged mercury and the ion, this is like acid. Into this double bond, if you add mercury, then that acts similar to proton. So that binds to some position and then generate carbocation among these two positions. Which way? This way, because that's a more substituted position. Then mercury added here, and then water attacks that position, and here, then mercury is removed. Then your product is this one. Result-wise, this is similar to this reaction. By adding acid and water, then you get the product, but this is much milder conditions, and you can use in the laboratory. Okay, so in principle, this is similar to acid activated and adding water. As a result, one water molecule is added. That's why this reaction is called as hydration. Okay. So this reaction, if you look at the step by step, mercury is added first, and mercury is forming this kind of intermediate, and then the OH attacks to more positively charged position here, and then removing this mercury, we need to use this basic workup, the reductive workup. That reagent is called the sodium borohydride. For now, let's not worry much. That's a kind of a workup situation. Okay. Then you remove that mercury and it generates the proton here, hydrogen here. Okay. For now, let's focus on this part. Activate the alkene with the mercury and water addition. And product-wise, this is Markovnikov or not? Is this Markovnikov? No. More subsolid position is this, right? On that position, OH is added. That's Markovnikov. So far we have learned only Markovnikov cases. HX and Cl2, all of those cases, Markovnikov product. Now, next example is opposite. Now here, instead of mercury, we add a boron reagent, BH3. Then, this addition happens like this. And here, BH2 is added to less substituted position, and more substituted position is H is added. And workup is oxidative workup. This was reductive workup. This is oxidative workup, hydrogen peroxide, oxidant. Then remove this and then adding OH here. How? This OH and H2O attack this position and rearrangement happens. Remove this and OH is added here. Mechanism. So first of all, this BH3 is only 6 electron. That's acid. And that acid can take this lone electron from solvent and can be stabilized this way. This is the acid-base reactions. Acid-base means they can be dissociated and regenerated this one, right? Acid-base is a catalyst. It does not permanently donate. Temporarily donate and stabilize before reaction, it comes back to this reagent. And here, this reagent, if it is added first, BH2H, similar to this reaction. After this reaction is finished, still there are another BH, right? And one more BH here. So that means one BH3 is equivalent to 3 material of this. So one added here, and the other one also added here, and the other one also added here. So that means this reagent, you need to use only 1/3. It can react with 3 of these molecules. Okay? Once it is formed, now by adding hydrogen peroxide and break, and then all of the positions, adding OH. And the product is hydrated product. Now, if you look at the position of addition, in this case, BH3 seems like they are added, simultaneously added. And then this addition is more substituted position, more bulky position. Next page. Here, when they are added, they are adding simultaneously. That's why this is BH2 is bigger than hydrogen. So this is more steady positions, more crowded. That's why proton is hydrogen is donated to this position, and less substituted position BH2 is added. And workup by adding hydrogen peroxide, this is replaced by OH. Then, as an end product, starting from here and the hydration reactions, OH addition position is not more substitute position, this is a lesser substitute position. Result-wise, this is anti-Markovnikov product. It's the opposite to mercury situations. Look at the explanation again. Why this happens? Here, there's no carbocation intermediate. And addition, BH3 is added together. Now, the bulkiness of this material, hydrogen versus BH2, more bulkier one is preferred, less hindered position. And that position is replaced by the OH, and on the same side, so this one is added together, syn addition, not anti-addition, right? Syn addition, 말 배웠나? If those two motifs is added in the same direction, it's called as a syn addition. If it goes bromium intermediate and then attack from behind, the end result is like this, right? This is the anti-addition. Same direction, syn addition. So in this case, the first addition is a syn addition. And then this is replaced with OH. That's what happened. So as the end result, now we have two selective hydration. The method is possible. Starting from here, this is more substitute position, this is less substitute position. If you wanted to add OH this side, Markovnikov product, then we use this mercury method. If you wanted to have opposite direction here, if you wanted to have an OH, then we use this boron gradient. So this reaction is called hydroboration. The first step is hydrogen and boron added first. And by this workup, we get the OH. So by just looking at the first step, hydroboration, hydro is a hydrogen here. And this the method, by adding mercury, but the mercury is changed by oxygen later. So this method, historically they said oxymercuration. Just the naming. But anyway, the reagent wise, Markovnikov product and boron, the anti-Markovnikov product can be formed. Okay, to make this molecule from alkene, how can you do? You can think the reverse reaction first, then that reverse reaction is the dehydration. By removing this hydroxyl, we generate double bond. Then that double bond forming can be done next to carbon hydrogen, either this one or this one. Remove this way or remove this way. Then double bond can be formed here or here. Right? Two options. So these are those two options. Double bond can be here or here. Which one do you choose to make selectively this product? If you look at this one, this is two position substitute. This is one position. This is more crowded, more substitute position. This one, even though there is a branch position here, this is also one substitute. This is also one substitute. So then, Markovnikov rule may be less effect on this position. Right? Then if you choose this intermediate or this starting material, most likely you will get mixtures. One added here and one added here. Maybe 40%, 60%. But this is not clear. But this one is clear because this is disubstitute. This is a single substitute. If you choose this one to get this product, which method should you use? Boron method or mercury method? It should be boron method, right? This is a less substitute position, and this is the reason. So this is how you design your reaction. You have the product you want to make. Then you need to think what can be the precursor or starting material to make this material. And then you think maybe two possible pathways, and out of those two, which pathways you take, then you need to think about the selectivity. Using which method I can get dominantly one product. Okay? So far, that's a review. We just added one more, learned one more reaction, hydration. To the double bond, H-OH, hold together one water molecule. And position, Markov-Nikov position or anti-Markov-Nikov position. That's what it is about. 좀 복잡해 보이지만 이렇게 정리하면 그렇게 많이 배우는 건 아니야. Adding water molecule. Okay. Now next step is reduction. Reduction 나왔으니까 다음 번은 oxidation이겠지. So the two more reactions we are going to learn today is reduction and oxidation. Reduction. To the double bond, if you add two hydrogen, so that's a reduction. Can you define that's a real reduction? What is the oxidation number of this carbon? If this is a carbon, oxidation number of this carbon? 0. If it's 2, forget about this. If you add two hydrogen is added, then what is the oxidation number for this? +1, -1. Right? So electronegativity of this is 2.5, hydrogen 2.1. So this is more electronegative, attracted the electron. So that's why this is counted as -1. That's why this is reduction. If it's added oxygen there, then there should be oxidation. Oxygen is more electronegative. That should be +1. Right? That's oxidation. Adding hydrogen is a reduction. Okay. This reaction, how can you do? Utilizing catalyst. What kind of catalyst? Usually metal catalyst. Platinum, palladium, and metal itself, or sometimes metal or the oxide. With this kind of a metal reaction, seems like it can be added and to the same direction. Syn addition. Why syn addition? The metal catalyst, we can assume this kind of a big surface. And hydrogen, those two are the bond is quite strong too. But when they are attached to the surface on this metal, and it's kind of attached to the metal surface, and it's kind of activated this way. So this HH bond is becoming weak. And then this double bond approach on top and captured two hydrogen together. So if it added together, we can imagine there's more syn addition, right? Not anti-addition. Big surface and hydrogen is deployed like this, and then double bond approach and take one each, syn addition. Makes sense, right? Result is really syn addition. And if there is an option that, in this case, option of hydrogen the approach is from top or from the bottom. Even syn has two options, from top or from the bottom. In this case, which side is more accessible to the surface? This side is more open, this side is a little more crowded, and if there is a big metal surface here, maybe difficult to access this direction, maybe easier to this direction. That's why hydrogen approach from here rather than here. Also of them are syn, but if you look at the selectivity, this one is more preferred. Makes sense, right? So in this case, this is syn addition because the two hydrogens is added together from the same surface. So example of this, any double bond, maybe hydrogen can be added. But hydrogen, this is equivalent, right? Not polar. This is a non-polar. That's why non-polar prefers non-polar. Polar prefers polar. Makes sense, right? Polar has a plus minus, then minus may attack the plus. That's a polar addition. That's why even though there is one double bond and two double bond here, this hydrogen can be added here, not here. This is a more polar bond. Similar situation, not here, it is added only to CC bond, CC double bond. Same situation here, CN is also similar to CO, and is more electronegative. It's a polar bond here, so that's why non-polar bond. Selectively, it attacks only carbon-carbon double bond by adding two hydrogen syn addition. Okay? Then later you may learn some other method to selectively reduce this part, maybe polar reagent, not non-polar reagent. Okay, that one we don't know for now. Now, this kind of dehydrogenation is very common in food chemistry, especially for making margarine. In English, margarine. margarine 만들 때 you can get the 식용유. 식용유 has a lot of this kind of double bond. With a double bond, they becomes more flexible, so they becomes a solid, that's the solution. And if you reduce this double bond, then they becomes saturated. Saturated one becomes more solid, like the vegetable. Okay, and margarine is artificially made butter by reduce this double bond into this saturated bond. Very interesting. In our body, those double bond is all of them, most of them, we found that they are cis configuration. So cis fatty acid is the component of this. But during this reduction reaction, sometimes those reaction is not completely, and during this catalyzed reduction reaction, sometimes those cis bond becomes isomerized to trans, and it can generate trans fatty acid. You may have heard many times, but bad for health, the trans fatty acid, trans bond, is formed by this kind of a fluid process. During those activated hydrogen, it is fully reduced, that is okay. But once it forms this kind of isomerization, then this artificial material can be generated. Okay, so this is the process of the reduction of the fatty acid. Now in nature, we don't have platinum, palladium kind of metal catalyst. We have a reducing reagent, so-called NADH or NADPH. One NADH is the reduced form, is a higher energy. One NADH, if you learn biochemistry, one NADH can generate how many ATP? It's a more? 2.5, approximately 3 they say, depending on those efficiency. One NADH can generate 2.0 or 3 ATP. That's a much higher energy material. And this NADH is the source of H minus, and then it can reduce this bond. By looking at this reaction, how many electrons is transferred? How many hydrogen atoms is transferred? 식에 다 써 있는데. 2 hydrogen. I see only one hydrogen is added here. The other hydrogen is donated by, from solvent, H plus is donated. Electron, H minus is transferred here, 2 electrons is transferred. So that's why if you look at the biochemical pathways, NADH reactions usually they draw like this. 2 electron, 1 hydrogen transfer, or combined together. Effectively, this is a hydride. 2 electron, 1 hydrogen atom. H plus does not have any electron, right? H plus together with the 2 electron, there is a hydride. Effectively, this is a hydride. 1 hydrogen atom, nucleus plus 2 electrons. That is the NADH reaction. Okay, reduction done. So for now, we just learned only one chemistry. Metal surface metal catalyst and then adding two hydrogen together. Syn addition. Okay. Oxidation. If you add H2O2, or one side is replaced with the R group, ROH, then onto this double bond, this one oxygen is inserted as a bridge. This kind of a bridged molecule we call epoxide. That is the product. One oxygen is inserted in the middle, similar to chromium salt. For chromium is unstable intermediate. Epoxide is reactive but more stable than chromium. It can be isolated. Reaction mechanism is like this. Again, this lone pair, the pi electron is a nucleophile that donate electron first, and then push, and then this oxygen coming back and forms this product. Reaction was similar to Br2 reaction. The product is oxygen, not Br. So this is the one way. You have double bond, you add peroxide, ROOH, which is similar to H2O2. Okay. Then one oxygen is donated as cyclic insertion. That's oxidation. For both carbon, this one, both of them are now +1. That's why oxidation. Another method to make the epoxide is by adding chlorohydroxyl first. So with this reaction we have learned, right? First step is by adding Cl2, activate this one, Cl plus here, and water attacked behind. So this is a trans product, not cis product. And then here, if you have a strong base, then by removing this H and then this O attack here and push this out. So this is from the top attack, and then Cl minus moves to behind. So direction is correct. Moving here in the same direction, Cl minus moved out. And the product is that this remains here, and then oxide is formed. And the result is the same. Previous one is also from Syn addition. Just added directly one oxygen from the top. Syn product, cis. Here, first step was making trans, but this one attacked from top and eventually make the syn. Two-step reactions. Okay. So this is the way to make the epoxide. And once it forms the epoxide, similar to chromium salt, if you add water here, water comes in and attacks behind and pushes this out. Previous reaction, it was a bromine here, so BrOH, right? Now here, O was here, that's why product is also OH. But mechanism is very similar to bromine reactions, which is similar to this. So previously, we have seen Br2, and Br first one is added, and then Br minus come behind and then open out. This is the trans product of Br. Oxygen here first, and then water comes behind and attack here, trans OH. Okay? If you compare those reactions and then try to follow what is the logic, how it was made, that would be easier than separately to memorize. Okay? 조금만 다르지, 많아지려고 한다지. 조금만 다르지. Okay, here, now into this, the double bond, H2O2 addition is just adding one oxygen. And then you can add the water, and then you can open out, making the trans OH. In this case, two oxygen together using this osmium tetroxide as a reagent. Osmium tetroxide has 4 oxygen, so 2 oxygen can be added together, forming this intermediate. and then work up by cleavage here. Reductive work up. Then forming this hydroxide. Product wise, what's the difference of this product from previous method? This is cis addition. Right? OSO4 is added from the same side. That's why the end product is cis. By looking at that reagent, if you can catch that point, then that's enough. Okay? Previous one, adding one oxygen molecule, one oxygen atom, and then open up from behind. Then you get trans. In this case, adding two oxygens together. Now, a little modification of this reaction. In this case, OSO4, number one, very expensive. Number two, very toxic. It can attack any double bond. We have a lot of double bond in our eyes. That means it's very toxic to the eyes. So you don't want to use an excess amount of OSO4. This is reductive way you destroy this reagent and generate the OSO2. That's a dead end. To recycle this by adding OSO4 reaction, but by adding this N oxide of NMO, this is another oxidizing reagent, donating this oxygen to this intermediate and regenerate this OSO4. This is a co-oxidant to regenerate OSO4. First step, you need OSO4. But to recover this one, by adding another oxidant, you can regenerate this one. Then you get same product, but in this case, you can use a very small amount of catalytic amount of OSO4. 스키면 들여다봐야 알겠지만 무슨 이해하는지. OSO4 is expensive. That's why by adding another oxidant to recycle it in the middle of reactions. Okay. Again, product the same. cis product. 조금만 더. So this is the addition of oxygen. We learned two oxidations. One was adding one oxygen atom. The other one is adding two oxygen atoms together. Okay? So this is addition reaction. Now, cleavage of that double bond. We have double bond here. If you add ozone, cousin of the oxygen molecule. By adding ozone, this ozone is making this kind of intermediate, and this mechanism is complicated and forget about it. But if you add ozone, then it is breaking in the middle, and then adding oxygen in both sides. And in this case, you can do both reductive workup or oxidative workup. If you add a zinc, this is reductive or oxidative. Reductive, metal powder reduction. Okay. If you add metal powder reductive of the reagent, then only oxygen is added for each positions. Let's look at the example. Double bond here. Ozone and number one, number two means that's a stepwise reaction. Number one reaction done first, and then second time you add zinc, separate reactions. That means okay, that's a stepwise. Then product is cleaved in the middle, oxygen added here and oxygen added here in both sides. So ozonolysis we call. Olysis means it's breaking. By adding ozone and we break it. Ozonolysis. Hydrolysis. By adding water and break it. That's a hydrolysis. Okay. Ozonolysis by adding ozone and break in the middle. And if you have a double bond here, if you have this kind of polar bond, it doesn't touch. Ozone is also added to CC bond, and then break in the middle, oxygen in both sides as a double bond. That's ozonolysis. Very similar reactions can be done by strong oxidant, permanganate. Permanganate maybe you have learned, used in middle school to generate oxygen gas. Strong oxidant permanganate, if you add similar reactions, you can break this out. But in this case, this is oxidative workup. Oxidant and oxidative method, and generate not only oxygen, but also apply this extra OH there. Previous case, you added only one oxygen each, right? That's a reductive workup. If that is an oxidative workup, here you can add, in this case, it's a ketone, it doesn't matter. If it's an aldehyde option, then you can generate further oxidation aldehyde oxidized into acid. So up to here, break this up and then oxidative water. 2 oxygens each. And one more. Oh, 2 more. 3 more. Let's see. 아이씨, 또 있네. 요거까지는 해야 돼. 조금만 더 참자. 이게 마지막인 줄 알았는데. Okay, then second oxidation. First oxidation was adding 1 oxygen or 2 oxygen. Second type was breaking up the double bond, adding 1 oxygen each. Reductively, just 1 oxygen. Oxidatively, 2 oxygen each for the condition. And if you have a diode for iodate, IO4 reagent, make this intermediate, and then rearrange to open this up, and then generate all the oxygen double bond, oxygen double bond. This is IO4 reaction. It happens only in the vicinal 1,2 diode, and then we break up in the middle, and then generate the oxidative, the oxidation on this position and this position. So third types. So far, 2 reactions we have learned is to the alkene, to the double bond, 2 type of reactions. This third reaction is diol first. Then this diol could be formed by OSO4, right? The diol is formed, and then cleavage that in the middle by forming this intermediate. Intermediate shape is similar to OSO4 intermediate, but rearranged, and then this oxygen by breaking this, that means moving this, and then you break this out and then double bond the forming. This is the third type of oxidation. Now, to summarize this, ozonolysis and zinc work up, and you generate this product. What was the starting material? Ozonolysis was breaking up in the middle of alkene, right? Then you can connect this and this together. Then combining this together, this was your starting material. Good. 좀 많지? So let's summarize what we have learned today. Last week we have learned acid and chloride, HCl, acid activation, and carbocation formed, and chloride attack behind, or the carbocation side. Today, new thing we learned, Cl2. Cl is activating, or Br is activating by forming cyclic intermediate, bromium kind of structure. And then behind, Br can attack. Then Br trans. Or water can attack. Then BrOH. Similar situation. Okay? If it's just acid and then water, then acid captured and 1 water molecule attack, hydration. So that's what we have learned as first. And then reduction was on the metal catalyst surface. Hydrogen was activated, added syn addition to the double bond. That's reduction. We learned only one. Easy. Oxidation, 3 types. One type was 1 oxygen atom was added as a bridge, forming epoxide. And then ring open can happen. Then you can have hydroxyl, trans-hydroxyl. That was the type 1. Second type was OSO4. OSO4, 2 oxygen, syn addition. Right? So that was second type of oxidation. Third type of oxidation was a cleavage in the middle. Ozonolysis by adding ozone, oxygen. KMnO4 is oxidative workout. That's why if it is the ketone, then the ketone stop. But aldehyde, it can go further to the carboxyl acid. So that's oxidative cleavage in the middle. Okay, this is almost 2/3 of chapter 8. 조금 많은데 일단 여기까지고 한 1/3, 3분의 1좀 남았는데 unfortunately this week is 대한과학회 week. I should leave tomorrow. 이번 주 목요일에도 안타깝지만 또 비디오를 해야 될 것 같고 아직 녹화 안 했는데 내일 가야 되겠어요. 지금 가서 녹화해야 돼. 그래서 뒤에 남은 부분은 녹화해서 올려놓을 테니까 양은 지금까지 오늘 배운 거에 한 절반 정도밖에 안 되기는 해. 조금 남았는데 여기까지 해서 연습 문제 열심히 풀어야 될 거예요. 지금 몇 가지 컨셉, 세 가지만 한 것들이 많이 섞여서 나왔기 때문에 다음 주는 알카인 들어갈게요. 트리플 바운드. 알키는 여기서 서머라이즈 하고 서로 비교해가면서 연결해둬야 그나마 덜 헷갈리고 가지고 갈 수가 있어요. 한번 헷갈리기 시작하면 뭐가 뭔지 거기서 헷갈리면 답이 없어. 들어도 다 똑같은 얘기를 하는 것 같고 그런데 나는 답을 모르겠어. 자, 그 시츄에이션을 면하기 위해서는 이번 주말까지 알킨 복습 잘하고 문제 잘 풀기 바랍니다. 내가 문제를 올려놓기는 할 텐데 그 문제 매지 말고 풀 수 있는 만큼 많이 풀어서 문제 쭉 보면서 도움이 될 것 같으면 앞으로 가지고 공부합니다. 오케이? 그러면 만나기는 다음 주 화요일에. 오케이?